This talk will explain how CFD can be used to improve the performance of a pump oxygenator device. The title of the talk is Novel Flush Bearing Design Mitigates Thrombosis Formation in Vitro and in Silico. I am Greg Bergerine from Mississippi State University. Let me acknowledge my collaborators Ryan Orizondo, Bill Federspiel from the University of Pittsburgh, Mansour Zazupakov, and Jim Antaki from Cornell University. I have no disclosures. Let's discuss in detail the device under consideration. The device is the modular extracorporeal lung assist, a device developed at the Bill Federspiel lab at the University of Pittsburgh. It's an integrated device that involves a centrifugal pump, indicated by the green component, and a cylindrical fiber bundle, indicated by the blue component. Pertinent to this talk, the rotor of the centrifugal pump is supported by upper and lower ball and cup bearings. After performing well on the benchtop and in short-term in vivo studies, the device was evaluated in a healthy sheep model. The device was connected via cannulation using a dual lumen catheter. Anticoagulation was achieved through heparin infusion, and we sought to keep the blood flow at its maximum 1.5, 1.4 liter per minute rate without suction events. The initial design of the device did have a persistent problem. In particular, for Design 1, 3 of the 4 trials had significant thrombus at both the upper and lower bearings. This image shows a typical thrombus located at the lower bearing. Notice its large size, and the blackness of it indicates frictional heating damage. The presence and growth of the thrombus can be observed in the motor torque curves, which were anomalous from the outset. The large spike toward the end of the study is probably associated with thrombus-induced rotor seizing. High hemolysis also appeared to be another marker associated with thrombus formation. Now we will discuss how CFD helped drive the design changes for this device. These are plots of velocity vectors around the upper bearing, shown in the red box of the inset image. Design 1 had large flow separation downstream of the bearing holder, which are indicated by the blue colored vectors. These separation zones in Design 1 were associated with the formation of ring thrombus, given by the location of the red circles. We believe this thrombus embolized and caused problems later downstream in the pump. Our solution in Design 2 was simply to invert the ball and cup configuration, and as you see from the image, much stronger washing occurred on all surfaces, and it eliminated the flow separation. Design changes to the lower bearing are a little more complicated. Lower bearings in centrifugal blood pumps have always been problematic. Past attempts of solutions have included the addition of blades, undulations or other shape modifications, and also the addition of washout holes, often with hardly any improvement whatsoever. The basic issue with the lower bearing is that there is very low flow, stagnant flow around the lower bearing. we have developed what we believe is a novel bearing configuration consisting of 4 synergistic shape features. We have a patent pending on this idea. The 4 features consist of feature labeled 15, an axisymmetric cavity around the bearing, feature 16, which is a plurality of ports to centrifugally pump blood out of the cavity, feature 14, a tapered axisymmetric gap with decreasing gap toward the cavity to accelerate blood flow in that region, feature 17, which is a non-smooth, effectively discontinuous volumetric expansion into the cavity. The overall goal is to enhance washing around the lower bearing. These are CFD simulations of the change to the lower bearing. These are velocity vectors plotted at the same scale factor, so they are comparable. CFD shows that the washing of the lower bearing is significantly enhanced. These are velocity vectors that have been scaled 10x to show more detail. And we see it's very obvious that design 2 has much stronger flow around the lower bearing. So, how did design 2 perform in vivo tests? Of the 8 trials using the design 2 pump, 4 went to 30-day completion, 3 of those with a pristine pump, 1 with a slight thrombus at the upper bearing. 3 of the studies terminated early due to various issues. 1 study, trial 2.5, did have a thrombus at the lower bearing, but you notice that it is much smaller than what we were seeing before. The motor torque and hemolysis curves for design 2 raised no concerns. Now that we have achieved significant in vivo improvements, we will discuss how CFD can help explain the reasons for this improvement. We do this by using state-of-the-art thrombosis modeling. This model has been developed by the Jim and Taki lab at Cornell University. The model consists of a total of 10 species and biochemical agonists. This model has been applied with good success to realistic biomedical devices. The image on the left shows its application to the HeartMate 2 blood pump. These plots show concentrations of activated platelets in design 1 and design 2 cross sections. We focus our attention on the concentrations at the lower bearings, and we notice that there are identical concentrations in both designs. When we look at plots of concentration of the platelet agonist TXA2, we also see that there are almost identical concentrations at the lower bearing for both designs. For the platelet agonist ADP, we once more see that at the lower bearing, identical concentrations of this species. However, when we look at shear rate, we find now the main differentiating factor between the two designs. Design 1 has a much lower shear rate around the lower bearing compared to design 2. If we look at shear rate around the lower bearings in design 1 and design 2 in a little more detail, we can begin to draw conclusions. What we see is that higher shear rates are going to equal higher wall shear stresses. In fact, design 2 has 2 orders of magnitude higher shear stresses. This converts into stronger surface washing, which means enhanced erosion of deposited platelets. The low surface washing associated with design 1 tends to promote thrombogenic activity. In conclusion, CFD is a useful engineering tool to design modifications as well as explain device performance. The thrombogenic performance of the Mod-Elast device has been significantly improved by CFD-guided design changes to both the upper and lower bearings. And what we found is that stronger surface washing at the bearings leads to more vigorous erosion of deposited platelets and therefore inhibition of thrombus formation.